In our first session, we talked about the Internet as being a network of networks. And those networks are generally organized into what are called autonomous systems. The autonomous systems are designated by provider, such as AT&T in this case. We see two autonomous systems, one for the US and one for Latin America. And they are really standalone networks that enforce the IP protocol at the edges, but internally they're managed by that single administrator and designed by that particular provider. The number, the autonomous system number, and we see three of them here, are assigned by the Regional Internet Registry under the rules and the pools that are set by IANA. There are both public and private autonomous systems, just as there are public and private IP addresses, and the private autonomous systems generally handle enclosed traffic, that is walled garden networks, or virtual private networks is a number used for private autonomous systems. Private autonomous systems can use the same physical network and the same routers as the public autonomous systems which serve the Internet. There are three methods of interconnecting autonomous systems, and from now on my comments will all apply to the public Internet and the public autonomous systems. The first we've already talked about, settlement-free peering. And settlement-free peering is conducted between Tier 1 networks, but it's also performed between a company like AT&T and their Tier 1 and Tier 2 networks. In Latin America, AT&T is a Tier 2 provider, and so they interconnect the Tier 1 in the US with that Latin American network. That's really a bridge more than it is a peering as it is in Tier 1. So we'd see a variety of traffic going across that Tier 1, Tier 2 network that AT&T would provide its customers. A second kind of peering is private peering. Now, private doesn't refer to private networks, but rather the fact that the arrangement between the two networks, AS1234 and AT&T in this case, is done on a negotiated basis. So the arrangements and the settlement fees are set between the two. It is for public Internet traffic, however, and in this case, the settlement agreement could mean that AT&T only provides connection to other Tier 1 providers and other ISPs and content delivery networks that are directly connected to the Tier 1. It might not include forwarding traffic and receiving traffic from the Tier 2 network in Latin America. That's all a function of the arrangement between the companies in private peering. A third and very popular kind of interconnection is public peering. And public peering occurs at inter-exchange points, IXPs. Those used to be called Network Access Point, NAPs, but the name has changed to IXP. An IXP is generally run by a nonprofit group that is facilitating exchange of traffic among networks. And so it essentially looks like a large Layer 2 network that provides Layer 2 connectivity between all of these companies. In the inter-exchange point, we would see hosting companies like Amazon and GoDaddy and Rackspace coming there with facilities that would connect at one physical location. We would also see content delivery companies like Akamai and Limelight, and would see ISPs. Those are all connected, as well as Tier 1 networks at particular physical locations around the world. These companies, like the hosting company and the ISPs, have a choice between buying facilities to get to the IXP or contracting on a private peering basis with a Tier 1 provider like AT&T. In the next slide, we're going to see how these interconnections actually function from a protocol viewpoint. In my example, I'm going to be a user sitting in an autonomous system 1234 could be an ISP, or it could be at an enterprise that's contracted with AT&T for internet service, and I want to access a website in Japan, and that website is for orchids, for exotic flowers and orchids in particular. So we're going to go through, first of all, the steps that the website administrator would have to go through to put their site on the network and get it advertised, and then we'll go through what a connection looks like. We first have to build connectivity. So Orchid, that is the company that wants their content on a website, has to select a hosting ISP and then get an address from that ISP. The ISP gets the address blocks from the regional internet registry. In this case, it's the Asia Pacific registry, which is called APNIC. As a side note, IPv4 addresses were exhausted in Asia Pacific about a year ago, so this would have to be from a pool that the ISP has and is not exhausted. Otherwise, you're going to have to go to IPv6, which we'll talk about a little later. The next thing that needs to happen, once that address is allocated, and here's the IP address, it has to be registered in an authoritative DNS. That's done so that all the other DNSs on the internet can find the IP address through the process that was described in the previous session. Now, the address has to be advertised. The DNS lookup that's going to be performed when I try to access that website is only going to return the destination IP address. It's not going to tell me how to reach it. The protocols used to advertise addresses are called border gateway protocols, and we're going to examine two of them here. One is an external border gateway protocol, so that is a protocol for exchanging address availability across ASs. It is not a routing protocol. It's strictly used to expose addresses and identify where connectivity, or reachability I should say, is possible. So in this example, AS2914 would send an eBGP message to AS7018 at the peering router that would have its own AS in the message, as well as, in this case, I'm going to say a subnet, 203, 183, and 38. The eBGP is generally not used for individual addresses, but range of addresses. And in fact, it would probably be a much wider range than I've shown here, but that's what I'm going to use in our example. The eBGP update only brings the information to the edge router. The AS7018 has to update all the other edge routers within its network so that all of the edge routers are in synchronization and they all know the edge router that is connected to this particular IP address, and this would be our egress router. So this is our egress router. The ingress router will be a function of where the incoming traffic is received. So now we've updated the egress edge router and updated all the internal edge routers in the AT&T network. The edge routers in turn update all of their eBGP peers, that is all of the CE routers and all the interconnecting routers that accept BGP updates, and now the address is advertised into our 1234 autonomous system and via the eBGP protocol. So we've had three sets of protocol updates in order to get this information over there. The iBGP is done using the TCP protocol, as is the eBGP, and TCP is used because it can be done across networks and it's not a hop-by-hop arrangement. It's an end-to-end arrangement and it's reliable. So now we'll look at how the IP packet is actually forwarded. First, a DNS lookup has to be performed, And because ORCID has been loaded in an authoritative name service, DNS that serves our host machine will locate that record, that resource record, and return it and resolve it. And we described that in the last session. The CE router will receive an IPPU from the host machine as the default gateway, and because BGP has notified it that this address is in fact reachable via the AT&T network, it will forward that IPPU to the 7018 edge. So that would be forwarding to here. Now the PE router, because of IBGP, knows that this peering or bridge router is the egress. So it knows the egress router is right here. So it's going to forward that IPPU to this edge router. The forwarding occurs in a way that's specified by the autonomous system, and there's no particular requirement for it to use one technology over another. The most common scalable method of forwarding in these large Tier 1 networks is a protocol called Multiprotocol label switching. With MPLS, there's a layer below the IP layer called the MPLS layer, which forwards the IPPU, and it does not use a hop-by-hop OSPF forwarding, but rather a hop-by-hop MPLS forwarding based on tag switching. So I won't get into that here in a great deal, but from an IP viewpoint, the PE router sees the egress router is the next hop. MPLS handles the mechanics of getting the packet from the ingress router, which is here, this is the ingress router, to the egress router. At the egress router, the IPPU is forwarded to AS2914, and so now our packet has been delivered to the host destination. There's an ongoing really update that needs to be done in a MPLS network, and the internal label distribution is performed at each of these P routers. So we have provider edge router and P routers, which are the core routers. The MPLS updates are done by the MPLS protocol and by a label distribution protocol. So the labels tables, that is the tables that specify how you handle MPLS routing, is distributed using an internal protocol. OSPF would be one choice, IS would be another. That's more than we have time for in this session, but it's worth noting that there are other protocols operating besides just the BGP protocols and MPLS inside these networks. While this really design looks quite complicated, it's really quite effective. And it is effective because it scales extremely well. These networks scale to hundreds or even thousands of routers. And the reason it scales is that each network element only has a limited responsibility. These two edge routers are primarily concerned with reachability and forwarding across the boundaries. They only need to know about other addresses in the network as they're being informed by IBGP. The core routers, which are large scale routers, do not need to update their routing tables at all as regards to the external networks because it is really gateway edge routing protocol that performs the final resolution and advertises reachability. The core routers are really routed on MPLS and of course the internal OSPF routing in order to update the labels and other parameters and information within the core. So this is a great example again of segregation of responsibility in order to be able to scale. In the next slide, I'll show you one